Hi, I'm Ramal Chanti. Today we are going to explain the task number 1, the result of the frequency responses of the integration with two different sets, R and C combination. Now we can use op-amp and two resistance. One resistance is 1 kilo ohm and another is 2.7 kilo ohms. So now I am implementing the frequency responses of the integration with two different sets of R and C. Both sets of R and C combination result in integration circuits are evidenced by the 90-degree phase shift at all frequency. The magnitude of the gain decreases with the increases frequency following a 1 by omega relationship. The second set with first resistance 1.7 kilo ohms has a lower gain magnitude compared to the first set with resistance 1 kilo ohms, indicating that the second circuit indicating the inputs signal more slowly than the first circuit. So for the integrated circuit, I have taken the value of frequency as 100 volts. We can observe the peak to peak value on the screen. It is approx 196 kilovolts. Now on changing the frequency from 100 to 200 Hz, I have observed the peak to peak value in 76 MV. Now change the frequency from 200 to 300 volts. We can observe on the screen peak to peak value in millivolts, approx 560 millivolts, and now setting the wave as we can take an across peak to peak value. Now I am changing the frequency from 300 to 400 Hz. We can see the peak to peak value 740 millivolts.
Hello, I am Rathon Nitish. I am going to explain the question number 2 of this assignment. Here we are using the op-amp differential circuit. With the help of the circuit, we will analyze the input and output signals with sinusoidal and spiral waves of different frequencies. So, this circuit we are giving the input signals at one end and the capacitors at another end of the capacitor is connected to the inverter terminals of the op-amp. One of the resistance is connected to the internal terminals and the other end is connected to the output terminals of the op-amp. So we made the ground with the help of the DC power supply here and the non-terminal of the op-amp. We made the ground with the help of the DC power supply. Here the non-inverting terminals of the op-amp is grounded and we took the power supply of magnitude of between range 12 volts at VC terminal and we attached the output terminals of the op-amp to the oscilloscope to check the wave of output signals and attached the second channel of the oscilloscope in the line where we took the input signals of the generator, observe the wave of the input signals. So the yellow wave shows at the output of the experiment and the blue wave gives the input of whole experiment. According to the second question result, we have took here 1 kilo ohms of resistor and 100 nanofards of capacitor, and we have took the frequency about 800 and the amplitude about 1 as a sine wave. We can see the difference between the input wave and output wave, but if we took square wave, then we can see a spike between them. So we can say that it is a differentiation wave. If we take sine wave as a differentiation, then the quotient will be come as output. And here we can say that sine waves will change, but square waves will not change.
Hi, my name is Rapur Ganesh. Today I am discussing about the third question. So, in the case of we are seeing with the third question, here we can see that uh, we want to define an operational amplifier and its basic characteristics and highlighting its versatility in various circuit configurations. So, first of all, we can discuss about the circuit design. So, in the circuit design, we want to use an op amp in an inverting amplifier configuration. So, and after input the two sine waves which are 1 kilohertz and 3rd kilohertz. I mean that 100 kilohertz to 300 kilohertz to the op amp through resistors. So we want to calculate the resistor values using the formula for the inverting amplifier gain. So here, while we want to calculate these formulas, we want to use the formula for the inverting amplifier gain. So using a capacitor in parallel with the feedback resistor to convert the output to the average value. So after we focused on our results, so we can show that the oscilloscope screen displaying the input sine waves. And another point, the oscilloscope screen displaying the output waveform which should be the average value of the input sine waves with the same phase. So and while we see to the conclusion, in the time of conclusion, we had successfully designed an op amp circuit, and it is capable of calculating the average value of two sine waves while preserving their phase relationship. So totally, the utilization of an inverting amplifier configuration and also careful selection of resistor and capacitor values, we achieved a synchronized output waveform displaying the average value of the input signals. This demonstration highlights the versatility and effectiveness of op-amp circuits in signal processing applications. So we can encourage viewers to explore further and experiment with different frequencies and amplitudes to deepen their understanding of op-amp functionality. Thanks for joining with me and discussing about that.
Thanks for giving this opportunity to explain this question.